Dear students, in this video we are going to learn about quantifiers and some of the proofs of theorems. Okay. So what is quantifier? Before we get into quantifier, we should know what is an open statement. Open statement is nothing but a declarative sentence will be there. It is called as an open statement. It must contains one or more variables. Okay. And it is not a statement, but it becomes a statement when the variables are replaced by certain allowable choices. That means, see here, we are having one sentence, p of x, right? What is p of x? It is the number x plus 2 is an even integer. So here the restriction, that is allowable choices, are universe set. What is universe? It is given a set of all integers. You can take integer value for x. Okay, so here if you take p of x as, instead of x, if you put 1, what is p of 1? It is 1 plus 2 is an even integer, right? This is the actual statement, but here 1 plus 2 is 3. So 3 is an even integer. This statement is a false statement. Okay, so this is how you have to find the truth value of an open statement. It becomes an open statement. Why? P of x is an open statement because we can assign any value to x from the restriction. What is the restriction given? It is universe set. Universe set is set of all integers. So in the same way, if you give q of x comma y is given here as the numbers x minus y, y plus 2, x plus 2y, right? So if you take x value as 4 and y value as 2, what is q of 4 comma 2? It is the numbers x minus y is 2. Y plus 2 is y is 2. 2 plus 2 is 4. X plus 2y is 4 plus 2 into 2 is 8. So these are all even integers. So q of 4 comma 2 is a true statement. Okay. So this is a open statement. Q of x comma y is an open statement. Here it contains two variables. Okay. One or more variables should be there. You have to replace these variables by certain allowable choices. These two are called open statements. Okay. Examples of open statement. So here what is a quantifier? So in this case we have given some values for x and y, right? 4 and 2 are the given values here. So if you, for some 4 and 2, the statement becomes a true statement. So for some values of x, for some value of y, the statement is a true statement, right? So this is how you have to quantify an open statement. So there are two types of quantifier. One is an existential quantifier and another one is an universal quantifier. What is existential quantifier? Only for some x, for at least one x, there exists an x. These are all meaning the same only. So for some x, the statement must be true. Okay, so it is represented by there exists x. If it is two variables, there exists x, there exists y. So universal quantifier is for all x, the statement must be true. For all x, for every x, for any x, all meaning the same. So for all x, for all y, the statement must be true statement. So for example, here we are having open statement p of x, q of x, r of x and s of x. We have to find the truth values of all these. Okay. So first, what is universe? You have to identify universe. Consider the following open statement on set of all real numbers as universe. So we have to consider universe as real numbers. You can take choices for x and x as real numbers. Okay. So first one is for all x, p of x implies q of x. What is p of x? X greater than or equal to 0. Q of x is x squared greater than or equal to 0. So p of x implies q of x. For all x, we have to prove. So when you will get 0, in the case if the first sentence is true and the second sentence is false, in that case only you will get 0 for implication, right? PQ, if P is true and Q is 0, then only P implies Q will become a false statement. So you check here when P will be true. See here, if we are having P of x is x greater than or equal to 0, we have to prove it for all x. What is this quantifier? It is a universal quantifier given here. So P of x is x greater than or equal to 0. So if you give 1 as the value of x, 1 is greater than or equal to 0 is a true statement. Okay, so what about q of x? Whenever p of x is true, obviously you will get q of x is true. Why? Here x is greater than or equal to 0 is the open statement. What is q of x? X is squared greater than or equal to 0 is the q of x, right? So obviously any value, if you take, if it is positive, then its square is also a positive. It depends on the statement, so you have to check with the statement, and quantifier also you have to see. If it is implication, you have to go with this condition 1. If you have to get the value as 1, that is true statement you have to get for first one, and the second one you should make it as a false statement. If it is false, then you will get the whole statement as a false statement. But in this case, it is different. Whenever you are having a positive value, obviously its square is also positive. So q of 1 is also a true statement. Q of 1, it is 1 square greater than or equal to 0 is a true statement. This is the only case. If first statement is true, second statement is false, then only you will get false for implication. But we won't get the second statement as a false statement, because whenever a number is positive, its square is also a positive. In this case, q of x is like that. X squared is greater than or equal to 0. So what is the conclusion? It is for all x, p of x implies q of x is a true statement. It is a true statement. So second one is there exists p of x and q of x. So for this case, you have to, there exists is here. So existential quantifier. So you can take only one value of x so that the statement should be true. So if there exists an x, then you can conclude that the statement is true. Okay. So there exists x, p of x and q of x. Okay, p of x is x greater than or equal to 0, and q of x is x squared greater than or equal to 0, right? So we have to prove that existent for some x, for at least one x, the statement is true. So if you take x value as 2, what is p of x? It is, it will become, x will become 2. So 2 is greater than or equal to 0. So instead of x, we will be having here 2. What is q of x? It is 2 squared greater than or equal to 0. So in this case also it is true. Here also it is true. So true and true will become a true statement. We need not prove for all x. It is, we have to show at least one x. So we have shown that it is for x is equal to 2. Both the statements are true. If p of x is true, q of x is true, then we can conclude that p of x and q of x is also a true statement for an x. There exists an x. This statement is a true statement. Okay. So in this way you have to see to the truth value of the statement. So third one is for all x, q of x implies s of x. What is q of x? It is x squared greater than or equal to 0. S of x is x squared minus 3 greater than 0. We have to see to the implication statement, and for all x it is universal quantifier, right? So for all x, for all x, we have to prove q of x implies s of x. What is q of x? It is the statement x squared greater than or equal to 0. What is s of x? X squared minus 3 strictly greater than 0. Okay. So if you have to show that implication statement, this is an implication statement. If it is implication statement, you have to take in such a way that first statement must be true statement, and you have to bring the second statement as false statement, so that you can show that it is a false statement. Okay, so this is the only case you have to check for implication statement. It is for all x you have to prove. So you have to take every x and you have to prove. So we are going to give a counter example and we are going to prove. Okay, so here if you take x as 1, what is q of 1? It is 1 squared. 1 squared is greater than or equal to 0. It is a true statement. But here s of x, it is s of 1, it will become 1 squared minus 3. What is it? It is 1 minus 3 is minus 2 greater than 0. It is a false statement. So true, false. So what is this? It is an implication statement, right? So q of 1 implies s of 1. It is a false statement. So for every x we have to prove q of x implies s of x is a true statement. But we have here x is equal to 1. For x is equal to 1, this statement becomes a false statement, right? So for all x, q of x implies s of x is a false statement. Okay. So fourth one is for all x, we have to prove r of x or s of x. What is r of x? It is x squared minus 3x minus 4 is equal to 0. And s of x is x squared minus 3 greater than 0. Okay. So next one we have to prove for all x, r of x or s of x. What is r of x? It is x squared minus 3x minus 4 is equal to 0 is r of x, right? What is s of x? It is x squared minus 3 is strictly greater than 0. So we have to check for every x here. That is for all x, the statement should be true. So or means either one of them is true, then you can make it as a true statement. Okay. But we have to check for false. Okay. So here if you are having for all x, then it should satisfy for every x, right? If you take value as 1, okay, so it will become r of 1 will become 1 squared minus 3 into 1 is 3, 3 minus 4, which will become 1 minus 3 minus 4. So it is minus 6, which is equal to 0 is a false statement. This is a false statement. Okay, what is s of 1? If you take x value as 1, what is s of 1? It is 1 squared minus 3, which is equal to minus 2 greater than 0 is also a false statement. So in this case r of x or s of x, both are false statements. So you will get the statement as false. R of x or s of x, for all x, for every x, it is a false statement. If there exists x, they have given existential quantifier. In that case, we can give one counter example so that the both of the statement can be true. But here the quantifier is for all x, that is universal quantifier is given here. Okay, so this is a false statement. So next example, here we are having universe as non-zero integers. Here all non-zero integers are universe. Okay, so you can take the values of x and y as non-zero integers only. Okay, so here the first question is there exists x for all y, xy is equal to 2. For all y, xy is equal to 2. So there exists x for some x, for some x is equal to, we can take any value. You can take x is equal to 1. For all y means any y value you can take. So y is equal to 4 if we are having y value was 4. Then what is x into y will become? Xy will become 1 into 4, which is not equal to 2. Right? 4 is not equal to 2. So in this case, it is a false statement. Since we are having for all y, it is a false statement. So this statement is a false statement, right? So next one is here. For all x, there exists y, xy is equal to 2. So similar way, we can prove for all x, there exists y, xy is equal to 2. So you have to give counter example. First you take there exists y for some y. For some y is equal to, you can take any value. For some y means if it is 2. Okay. For all x means any x you can take. So if x is 3, then what is xy? You have to try to prove that it is a false statement. Say in which cases it will become false. And then we have to try for a true one. Okay. So xy is equal to 2 into 3, it is 6. So it becomes a false statement. So for all x, it is not a true statement. Okay, there exists y, there exists x. If the statement is there exists x, there exists y. In this case, it is a true statement. Why? Because we can take there exists x is equal to 1 for some x is equal to 1, and for some y is equal to 2, xy is equal to x into y becomes 1 into 2. In this case, it is a true statement. So if we are having there exists x, there exists y, xy is equal to 2, it is a true statement, right? But in the above case, it is a false statement. For all x, there exists y, it is a false statement. So it is third statement given here. There exists x, there exists y. 4x plus 2y is equal to 3. X minus y is equal to 1. So instead of giving p of x, q of x, they have given the open statement directly. They haven't given the representation. Okay. So here, what is the statement? It is there exists x, there exists y. 4x plus 2y is equal to 3. Okay, and we are having x minus y is equal to 1. Okay, so how you will find x and y values? There must be x, there is an x, there is an y, right? So how you have to find these x and y values? You have to solve these two simultaneous equations. So here we are having two equations, right? So solve these two equations. 4x plus 2y is equal to 3. X minus y is equal to 1. Multiply the second equation by 2. So what you will get, it is 2x minus 2y is equal to 2 if you multiply this equation by 2. So now add these two equations. 4x plus 2x will become 6x. So 2y and 2y will go off. 3 plus 2 will become 5. What is the value of x? It is equal to 5 by 6. Now you substitute the value of x in any of the equations. We can take this equation, x minus y is equal to 1. So what is the value of x we are having here? It is 5 by 6 minus y equal to 1. Okay. So what is the value of minus 5? It is 1 minus 5 by x. So you will get the value as 6 minus 5 by 6. What is 6 minus 5 by 6? It is minus y is equal to 1 by 6. So what is the value of y? Y is equal to minus 1 by 6. So x value is 5 by 6. Okay. And we are having y value is minus 1 by 6. But see to the universe set. What is given in the universe? It is universe comprises all non-zero integers. So you have to take only x and y values from non-zero integers. Okay. So it must be integer, right? So here you see it is not integer. Minus 1 by 6 is not integer. 5 by 6 is not integer. So we are getting for that there is no x and y exist for these two equations, so that it becomes an integer. So here these are all not integers, so the given statement is a false statement. So this is a false statement. False. It is a quantified statement. It is a false statement. These are all called as quantified statement. Okay. So here this is a theorem. Here you have to consider for even number n must be equal to 2 times of an integer, any integer, or okay. So if n is an odd number, then it is 2 times of an integer plus 1. Okay. So here first theorem is for all integers k and l, if both k and l are odd, then you have to prove k plus l is even. So what you have to take? You have to take k and l as odd numbers, and you have to prove k plus l is an even number. If k is an odd number, k and l is odd number, what we have to prove is k plus l is an even. Okay. So what is k? K is an odd number. So how it will be? It is 2n plus 1. You can take, if the given term is, it is in k, You can take it is odd form is 2n plus 1 for some integer n. Okay, so what is L? L is equal to some 2m plus 1 for some integer m. Okay, so you can have like this. So what is k plus L? What is addition of these two numbers, odd numbers? It is 2n plus 1 is k. What is L? It is 2m plus 1 is L. So you will get the addition is 2n plus 2m plus 1 plus 1 will become 2. So you can take 2 common. It is n plus m plus 1. Okay. If you take all the 2's common, it is an even number, right? What is 2 times of a number? It is always an even number. So k plus L becomes a even number. So when you add two odd numbers, you will get a even number. This is how you have to prove. So next theorem is for all integers k and l. If both k and l are odd, then kl is also a odd number. In other way also they can ask a product of two odd integer is an odd integer. Okay. So k and l are odd integer here. So what is the odd form? It is 2r plus 1. What is l? It is 2s plus 1. So instead of r and s, you can take m and n also. Any name you can give. Okay, so what is r? You have to mention it is integers. For some integer r, it is a odd number, right? So for some integer r and for some integer yes, what we have to find, it is kl is also an odd number. Okay, so here we are having k is odd number and l is odd number. What we have to prove is KL is also 1. K into L, it is multiplication. Previously we have done addition, right? So what is KL? It is 2r plus 1 into 2s plus 1. So it will become 4 times of rs plus 2 times of r plus 2 times of s plus 1. Okay. So what we are having here, it is 4, 2 and 2. So you can take 2 common. So it is 2rs plus r plus s plus 1. So in these three terms we have taken 2 common. So it will become 2 times of some number plus 1. It is an even number. Plus 1 means it will become a odd number. 2 times of any number is an even number. If you add 1 with that number, it is an odd number. So we have proved KL as an odd number, right? So this is the another theorem. Give a direct proof, indirect proof and a proof by contradiction for the following statement they have given. So what is the statement given here? It is if n is an odd integer, then n plus 9 is an even integer. So if n is odd, if n is odd, n plus 9 is an even integer. We have to prove. So what is this? This is p. If n is odd is p. N plus 9 is q. We have to prove p implies q. By taking p, we have to prove q. Okay. So this is the direct proof. First proof is direct proof. So how we can take n as an odd number? It is an odd integer. N is a odd number. Okay, it is a odd integer means how you can take it is 2k plus 1. N is equal to 2k plus 1 for some integer k. It is an odd number, right? Okay, so if n is equal to 2k plus 1, then what we have to find, it is n plus 9. So what is the value of n? So n plus 9 is equal to 2k plus 1 plus 9, right? So which is equal to 2k plus 10. 1 plus 9, it will become 10. So 2 if you take out, it will become k plus 5. So n plus 9 is equal to 2 times of k plus 5. What is this number? It is an even number. 2 times of any number is an even number, right? So what we have to prove actually, n plus 9 is an even integer we have to prove. So we have proved by direct way. So next way is indirect proof. They have asked for 3 proofs. One is direct proof, indirect proof, and proof by contradiction, right? So what is indirect proof? For indirect proof, we are going to prove it by contrapositive method. What is contrapositive method? It is negation Q implies negation P. What is the statement P actually we are having? It is n is an odd number, and Q, what we have proved in the last direct proof, it is n plus 9 is even, right? So here for indirect proof, we are going to prove by contrapositive way. So we are going to take negation Q and we are going to prove negation P. What is negation Q statement? It is n plus 9 is not an even integer. We have to take n plus 9 is not even, and we have to prove negation Q. What is negation P? We have to prove negation P. What is negation P? It is n is not odd. If it is not odd means it is even. We have to bring it even. So n plus 9 is not even means it must be odd number. So odd number means what is the form of odd number? It is 2k plus 1, right? So n is equal to 2k plus 1 minus 9. So it is equal to 2k minus 8. So if you take 2 common, it will become 2 times of k minus 4. So n is equal to 2k minus 4 means it is 2 times of some number is an even number, right? So which is nothing but even. So n will become a even number. So n is not odd means we have to prove it as a even number. So we have proved. Clear? So this is indirect proof. Negation Q implies negation P is an indirect proof. We have proved. And another proof is contradiction. We have to prove by contradiction way. What is contradiction? It is nothing but we have to assume that n is odd. This is the given statement. N is odd. Then we have to prove n plus 9 is an even. But we are going to assume that n is odd and n plus 9 is also odd. Okay. We are going to get the contradiction for this result. What we have assumed it is n plus odd, but n plus 9 is also odd. If it is n plus 9 is also odd, what is it? It is equal to 2k plus 1. You can write it is odd number. So n is equal to 2k plus 1 minus 9. So it will become 2k minus 8. So it is 2 times of k minus 4. What is 2 times of k minus 4? It is an even number where we have arrived, but we have assumed n as an odd number, which is a contradiction. Okay, so here we have arrived at contradiction. So which is a contradiction to our assumption. Contradiction to our assumption. What is our assumption? It is n is odd number is our assumption. Okay, so n plus 9 must be always, it is even. N plus 9 is also